Welcome to the video lecture for section 6.2. This is for MSc 1105. My name is Jorge Javier. So in 6.2, we're going to be doing one-to-one functions and inverse functions. So there are four objectives. We're going to determine whether a function is one-to-one. Then we're going to determine the inverse of a function defined by a map or a set of ordered pairs. We're also going to obtain the graph of an inverse function. And then we're going to find the inverse of a function defined by an equation. So the first thing is determine whether a function is one-to-one. So in this example, we can see that state is your domain, population is your range, and then each individual element in the domain is mapped to one individual element in the range. So they're all paired up, and there's nothing left in either one of these sets. So this is a one-to-one example of a one-to-one function. In this other example, we can see that dog and cat are both mapped to 11, duck, lion, and pig to 10, and rabbit to 7. So this is not a one-to-one function because the first thing is that the elements in the range do not equal the elements in the domain. So in this one we have 6, in this one we have 3, and then we have two individual elements in the domain that map to the same element in the range. So this is not one-to-one. So the formal definition of function is one-to-one if any two different outputs in the domain corresponds to two different outputs in the range. That is, if x1 and x2 are different inputs of a function f, then f is one-to-one if f of x1 does not equal f of x2. So here's another example. In A, this is a one-to-one. Again, you can see I have 3 elements in the domain, 3 in the range. They're all mapped individually, so that's a one-to-one function. For B, this is not a one-to-one function, so y1 in this example is the image or the output of x1 and x2. In other words, for this particular one, f of x1 is equal to f of x2, which is y1. And then for C, not a function, x1 has 2 images, so x1 maps to y1 and also to y2. x3 has an individual one, but again, I only have 2 elements in the domain and 3 in the range, so that's not going to work. Here I have 3 and 2, not a one-to-one. 3 and 3, they each map individually, so that's a one-to-one function. Here's another example. We're going to determine whether a function is one-to-one. So the following function, domain represents the ages of 5 males, and the range represents the HDL cholesterol scores. So for A, here we have the example, and you can clearly see that this is not a one-to-one function. Because 61 and 55 both map to 38, and then again, you know, these are kind of easy to count the elements. Some of them you can't, but here I have 5 and here I have 4, so I have to have one double up somewhere. And then for B, I have you can see -2, 6, -1, 3, 0, 2, 1, 5, 2, 8. So all of my elements in the domain, -2, -1, 0, 1, and 2 are unique. And then the elements in the range, 6, 3, 2, 5, 8 are also unique. So that is a one-to-one function. The next thing is the horizontal line test. So if every horizontal line intersects the graph of a function f in at most one point, then f is one-to-one. So you can see here clearly that this is not a one-to-one function. x1 and x2 are not equal to each other. However, f of x1 is equal to f of x2, which is h. We're going to also use the horizontal line tests for each one of these, A and B. A is f of x equal to x squared. B is g of x is equal to x to the 3rd power. So for A, you can see that f of x squared is not a one-to-one function. The horizontal line y is equal to 1 intersects the graph of f twice at 1, 1 and -1, 1. So f is not a one-to-one function. For B, we can see that the horizontal line test for g of x is equal to x cubed because every horizontal line intersects the graph of g exactly once. It follows that g is one-to-one. So here's the theorem. A function that is increasing on an interval I is a one-to-one function on that interval I. A function that is decreasing on an interval I is a one-to-one function on I. I hope you can see that because if each element maps to one individual element in the output, and so therefore they're either going to be increasing or decreasing in that interval. So here we're going to determine the inverse of a function defined by a map or a set of ordered pairs. And so what's the definition of an inverse function? Suppose that f is a one-to-one function. Then corresponding to each x in the domain of f, there's exactly one y in the range because f is a function. And corresponding to each y in the range of f, there's exactly one x in the domain, again, because f is one-to-one. The correspondence from the range of f back to the domain of f is called the inverse function of f. The symbol f inverse is used to denote the inverse function of f. That does not mean that is not an exponent. Unfortunately, the symbols are sometimes the same, but that does not denote an exponent. So it's not 1 over f. It's not the reciprocal of f. So here, find the inverse of a function defined by a set of ordered pairs. Find the inverse of the following one-to-one function. State the domain and range of the function and its inverse. So here we have the range for the original function is -3, -2, -1, 0, 1, 2, and 3. The range is -27, -8, -1, 0, 1, 8, and 27. And so the inverse of the function is found by interchanging the entries in each ordered pairs. So the inverse of the function, all you do is swap the x and y. So the domain of the function is -3, -2, 1, -1, 0, 1, 2, 3. The range of the function, -27, -8, -1, 0, 1, 8, 27. The domain of the inverse function is simply the range of the original function, and the range of the inverse function is just the domain of the original function. So again, domain of f is the range of the inverse function. The range of f is the domain of the inverse function. The reason being is because originally we have the domain of f maps to the range of f, and then what we do when we find the inverse, the domain of the inverse of f maps to the range of the inverse of f, which is the domain of the original function. So the inverse of f of x is equal to x, where x is the domain of f. F inverse f of x is equal to x, where x is the domain of the inverse function. So this is what we're talking about. And this is just another illustration of the previous example where the domain and range swap. Now, how do we verify inverse functions algebraically? So we're going to verify that f of x, which is 1 over x minus 1, is the inverse function of 1 over x plus 1. For what values of x is the inverse f of x equals x, and for what values of x is f inverse of x equal to x. So the domain of f, as long as x does not equal 1, the domain of the inverse, x cannot equal 0. So now, the composite of the inverse function f of x is equal to x, provided that x does not equal 1, and then f inverse of x is equal to x, provided that x does not equal 0. Now, we're going to obtain the graph of the inverse function from the graph of a function. So if the original function contains the point AB, then the inverse of the function contains the point BA. You can see that all we do is swap the x and the y. So the graph of a one-to-one function, f, and the graph of its inverse function, f inverse, are symmetric with respect to the line y is equal to x. And y is equal to x is this 45-degree line right here. So this is f of x. This is the inverse of f of x. So you can see a3, b3. So the domain here is a1, a2, a3. The range is b1, b2, b3. For the inverse, the domain is b1, b2, b3, and the range is a1, a2, a3 for this given example. So we're going to find the inverse of a function defined by an equation. So again, it's symmetric along the line y is equal to x. And so here's f of x, and here's the inverse of f inverse of x. And so we can do this algebraically. So the first thing that we do in y is equal to f of x, we interchange the variables x and y to obtain x is equal to f of y. So the original function y is equal to f of x. We switch the x and the y. So this equation defines the inverse function implicitly. So if possible, we'll solve the implicit equation for y in terms of x to obtain the explicit form of the inverse function, so y is equal to inverse of x. Then we check the result by showing that the two composite functions f inverse of f of x is equal to x and f of f inverse of x is equal to x. So here we have a function f of x defined by 2x plus 1 over x minus 1, where x does not equal 1. This is a one-to-one function. We're going to find the inverse. We're going to check the result. So first we replace f of x with y, and then interchange the variables x and y. So the original was y is equal to 2x plus 1 over x minus 1. Now we have x is equal to 2y plus 1 over y minus 1. We're going to go ahead and solve for y. And so we get that y is equal to x plus 1 over x minus 2. So the inverse function, f inverse of x, is x plus 1 over x minus 2, as long as x does not equal 2. And then we check them by doing the composite function, the inverse of f of x and f inverse of f of x, and then we both get x in both of these, so therefore these are in fact inverses of each other. So find the inverse of a domain restricted function. We're going to find the inverse of y is equal to f of x equals to x squared. X is greater than 0. Then we're going to graph the function and the inverse function. If you remember, at the beginning of the lecture we said that x squared is not a one-to-one function. But if we restrict the domain of it and otherwise just get a part of the graph, we can make it a one-to-one function within that restricted domain. So again, like I said, we can restrict the domain, we can make it a one-to-one function. So this results in a new function. It's increasing, therefore it's one-to-one. So then the function defined by y is equal to f of x is equal to x squared, as long as x is greater than or equal to 0, has an inverse function. So again, we replace y is equal to x squared with x is equal to y squared. Y is greater than or equal to 0. We solve for y to get the explicit form of the inverse. So because y is greater than 0, greater than or equal to 0, only one solution for y is obtained. So y is equal to the square root of x. So f inverse of x is equal to the square root of x. And then we check both of them to make sure that the composite functions of the inverse and the original function are both equal to x. And then they are, so therefore the original function y is equal to x squared, or f of x equal to x squared, where x is greater than or equal to 0, has an inverse function, which is f inverse of x is equal to square root of x. And this is the graph of the original function, restricted. So remember x squared, if we were to graph it completely, it would go this way and also up this way. And in this one, if we were to graph it completely, it would go here and then also have another part down here. But since we're restricted to make it a one-to-one, if I do a horizontal line test, f of x passes, and then that's the inverse function. And that's the end of 6.2. Thank you.